Hi. So today I'm going to talk about selection of views materialize. So this is a slightly more technical topic as compared to the other topics that we discussed in view materialization, and it's still an active problem, right? And it involves lots of concepts related to computer science, right? And I'll try to give you an overview of this problem. And the material that I've taken for this presentation is from a survey paper on view selection methods by Mami and Zora, and this was published in Sigmod Record 2012, volume 41, number 1. And so they have given a nice survey of view selection methods that exist in literature, and I have taken the main methods from there and try to give you an overview of the view selection problem in data warehousing. So the view selection problem is something like this. I've already given you some idea when I talked about view selection when I started talking about view materialization. So view selection problem is something like this. So for a given set of queries and a space constraint, and there can be other constraints as well, find the optimal set of views to materialize such that the benefit is maximized. So let me just explain this a little bit before I move on to the next few slides. So you are given a set of queries, so which is like Q1, Q2, Qn. Okay, and a space constraint. So I'm saying that space cannot be more than, say, space occupied by the materialized views has to be less than 10 GB. I'm just writing some numbers here. So what I want to do, I want to come up with a set of views, materialized views. I'll call them MV. So MV1, MV2, MVK. Such that the space required by these materialized views is less than 10 GB, and the benefit that I get, so this set of queries would have a cost, so I'll call it cost CQ, right? And there will be an average cost, so I'll call it average cost average cost of Q, right? So in the presence of these materialized views, I want to make sure that this average cost which I had or which I incurred without these materialized views is more than average cost Q in the presence of MV, right? So this is the objective, and I'm just working with a space constraint. There can be other kinds of constraints like the maintenance cost constraint, so this also has to be less than some value, right? So I don't want to spend, say, it could be in terms of time, I don't want to spend, say, 2 hours, more than 2 hours on every refresh cycle on maintaining the materialized views that I have created, right? So this is the problem. So I hope the problem statement is clear. So the objective is to minimize the average query processing cost that you have. So the queries are as I said, it's a set of queries. Minimize view maintenance costs, so which is mentioned here. Minimize space requirement, right? And so this problem is found to be NP complete, and so there has to be like finding optimal solutions can be very difficult or time consuming, so we look at suboptimal solutions using heuristic algorithms. So heuristic algorithms will come towards the end of this presentation. So let me begin by talking about the cost model. So the cost model is the weighted query processing cost. So query processing cost is equal to Qi belonging to Q, so that is for each query belonging to the set Q, FQi, which is the frequency of the query, and the cost of this in the presence of materialized views. So QC QIM is the processing cost corresponding to QI given a set of materialized views, because this query QI can benefit from multiple views, right? So there can be Materialize view 1 which helps part of this query. There is a Materialize view 3 which helps. So in the presence of these Materialize views, right, so what is the cost of this query, right? Okay, and there will be a cost in the absence of these Materialize views. So we have to basically look at the benefit ultimately, right? And FQI is the frequency. So if this query appears very frequently, then I give it more weightage, right? So that's how it is factored in. So FQI is the frequency of the query. So it also talks about the importance of the query in some way, right? Then we have this view maintenance cost. So again, it is very similar, right? So where FUVI is the update frequency of the Materialize view VI, and MCVIM is the maintenance cost of a particular view given a set of Materialize views, right? So again, it is quite similar to the query processing cost. Then let me begin by talking about static versus dynamic view selection. So these are the two different kinds of methods we have, right, or situations rather we have in the view selection problem. So static view selection approach is based on a given workload. So I assume that the workload is Q. Okay. So just a minute. So I assume that the workload is given to me. In a dynamic view selection approach, the view selection is applied as queries arrive. So I don't know what query is going to come next. So it is slightly more involved. So the workload is built incrementally and changes over time. And also because the view selection has to be in synchronization with the workload, any changes to the workload should be reflected to the view selection as well. So as and when there is a change in the workload, I should be able to change my views in such a way that the benefit is maximized. And in the dynamic setup, portfolio of Materialize views can be changed over time and replaced with more beneficial views in case of changing the query workload. So that's what I explained. So there are two aspects to this dynamic nature. One is that the workload is kind of not known to you. So each and every query is coming, you know about the query as and when it arrives. And the second aspect is that when the workload changes, say suppose you started with a workload Q, but now it has evolved to Q dash. So right, so then also you need to change the Materialize views to maximize the benefit. So static versus dynamic, continuing with that. So what we can do actually is we can start with the static approach, and when the average query cost goes above our threshold, we change the set of Materialize views. And we can do this by doing view selection all over again. That is, I take, so I had a query set Q, and I run the view selection algorithm on this and come up with the set of Materialize views, right? So either I do it like this, or what I do is, as I move from Q to Q dash, I incrementally change my Materialize views to MB dash, right? So I would want to do it incrementally, because running the view selection algorithm all over again could be very expensive. So I might want to do it incrementally. And a dynamic view selection is often referred to as view caching as well. So so this in the literature, a dynamic view selection is called as view caching. So view selection has two main steps. The first step is that we identify the candidate views which are promising for materialization, and techniques used for this are multi-query DAG, right? So DAG basically stands for directed acyclic graphs. Then there is a technique called as query rewriting, and then there is syntactical analysis of the workload. And once we have identified the candidate sets, then we run the view selection algorithm to get the materialized views, and this is typically done using heuristic algorithms as I explained earlier. So let me come to multi-query DAG first. So detecting common sub-expressions between different queries and capturing the dependencies among them. So this is a very important exercise, because I want to come up with views that can benefit multiple queries, and multiple queries would be benefited from a single materialized view only when they have similar sub-expressions, or common, not similar, common sub-expressions. So I need to do that first. So the dependence relation on queries or views has been represented using what is called as a DAG, and the most commonly used DAG is a and or view graph, right? So I'll give you an example of this in the next slide. So the union of all possible execution plans of each query forms what is called as a and or DAG, right? So I've given reference numbers. So the first number 1 is for this presentation, and 40 basically refers to the reference number in the original article, so that anything that you refer, you have a ready reference for that. So although, as I said, I'll not be giving you all the details of this because of time constraints, so I'll be just giving you an overview of this. So the first paper in which this concept was discussed was this 40, right? And the and or view graph described, so there is another way of describing it, which was given by Roy in the paper 2/42, is a DAG composed of two types of nodes: operation nodes and equivalence nodes. So I'll be talking about that. So each operation node represents an algebraic expression of the form select, projection, join, with possible aggregate functions allowed. And equivalence node represents a set of logical expressions that are equivalent. Logical expressions that are equivalent means they yield the same kind of result. So equivalence relations, if you have done relational algebra, you would know that what are equivalence relations in terms of relational algebra. The operation nodes have only equivalence nodes as children, and equivalence nodes have only operation nodes as children. So this is how it is defined, and the root nodes are the query results and the leaf nodes represent the base relations. So let me explain this using this kind of an example. So there are two queries, Q1 and Q2, and this is an example of a view graph and or view graph. So view V1 corresponding to a single query Q1 can be computed from V6 and V3, right? As you can see here, let me first clear the annotations. You can see V1, V6, where is V6? V6 is here, so I can compute it like this, or I can compute it, I go here and I go here, or right, or from R1 and V4. So there's another way of doing it. So V4 and V4 is V4, R1 and V4, R1 and V4. So this is what R1 and this is V4, right? So this is another way of computing this particular query. So if there is only one way to answer or update a query, the graph becomes AND view graph. Because if there are no alternate ways of evaluating a query, then it becomes a AND graph. So there will be no OR nodes in this, right? Or there will be only one way of executing a query. So the another way of representing the same information was given in a paper by Yang et al. In 3. Okay, so this is called as the multi-view processing plan, so MVPP in short, and it is again a directed acyclic graph in which the root nodes are the queries and the leaf nodes are the base relations from which they have been derived, right? And all the intermediate relations are only operators, which are SPJ. So you can see that what is happening is that Q2 can be evaluated by, say, if this operation, if I define this as so let me clear the annotations. So I can define this as a join. So Q1 can be obtained by joining R1 and R2, or there's an alternate way of computing Q2, that is applying some kind of say operation on R3, right? Similarly, Q2 can be a join followed by a selection, right? Okay, here also I can put a selection or a projection. Projection looks better, right? And then I have a operation between this and this, and before this performing join on R3, I perform a selection on R3. So this is how Q2 can be evaluated, and it may be just a projection on pi on R4, right? So Q2 could be so if I read this, so you can see this could be just a projection on R4, right? And I have a projection list, right? Or Q2 could be a projection, right, followed by a join between R2 and a selection on R3, like this, right? So you can see this is another way of representing the multi-query DAG, right? So this I have just explained to you, so I'll just skip the slide. Then the second approach after multi-query DAG is the query rewrite. So query rewriting based approaches not only compute the set of materialized views but also find a complete rewriting of queries over it. So in the first lecture on materialized views, I also mentioned about how the queries are rewritten using the materialized view. So this query rewriting does just that for you. So input to view selection is not a multi-query DAG but the query definition. So the input in case of multi-query DAG for the view selection algorithm is a multi-query DAG when we are using multi-query DAGs, but in this case it is the query definition. So I just look at the query definitions. What this query is trying to do. So the view selection problem is modeled as a state search problem using a set of transform rules. These rules detect and exploit the common sub-expressions between the queries of the workload and guarantee that all queries can be answered using exclusively the materialized views. So it makes sure that the queries that are there in the workload are executed whenever possible using the materialized views. And but what makes it complex is the completeness of the transformation rules, which make it exponential in nature. And then we have the syntactical analysis of queries. So the query workload is analyzed and a subset of relations is picked from which one or more views are materialized, if only it has the potential to reduce the cost of the workload. So it is done only if it has some potential. And however, the search space for computing the optimal set of views may be very large. So in most practical algorithms, we use the multi-query DAG as an input for the queries or for the workload. Then there are I'm just trying to give you the framework for the view selection. So there are cost models, then there are candidate view selection methods, and now we talk about or bring into the picture the resource constraints that we need to put. So there are three main models in the literature. So one is unbounded, then the second is space constraint, and the third is maintenance cost, that is the view maintenance cost constraint. So let me first talk about the unbounded model. So there is no limit on available resources, be it storage or computation, etc. So you assume that you can materialize as many views as you want, right? And view selection method thus reduces to minimization of the query cost and the view maintenance cost. So you can see here that I'm trying to minimize the query cost, which is this, which I have explained earlier, and plus the view maintenance costs, right? And there are two major problems with this approach, and it is seldom used. One is that selected views may be too large to fit into available space, right? Ultimately, it is just theoretically we are saying that storage and computation, etc., are unlimited space and unlimited computation power is available to you. But practically, what may happen is that you may want to materialize a view which you are not able to fit into available space, and the view maintenance cost may offset the performance advantages provided by materialized views. So if you remember, we talked about aggregates, a set of aggregates, and as I said, aggregates are also implemented as materialized views. So there was a case which I showed you, that you had a set of aggregates which took more than 24 hours to refresh, right? So the view maintenance cost may offset the performance advantages provided by the materialized views. So that's why we talk about some kind of constraints on both space and on the maintenance costs. So the space constraint model minimize the query processing cost plus the view maintenance cost under a space constraint. So I have only so let me first remove this. The minimization, this function remains the same. Only thing is that I've put a space constraint in this. So that's what we do in space constraint models. Then we have maintenance cost constraint model. So this you can either club with the space constraint or have it independently, or impose it independently. So what we have done here is that we have changed the minimization function, because which is the query cost only, and under a view maintenance cost constraint. So I put an upper bound to the maintenance cost, and you can see that this maintenance cost is the same, the expression is the same, right? So this is the maintenance cost constraint model. And then we have the algorithms for view selection. So there are 4 types of heuristic. As I told you, we use heuristic algorithms, and these heuristic algorithms are like deterministic algorithms, which are given in 4 and 5. And 5 is basically the A star algorithm, which I'm sure all of you would be knowing. Then there are a set of randomized algorithms. So here like the main randomized algorithms are like genetic and simulated annealing. And then we have hybrid algorithms, which take the best of deterministic and randomized algorithms. And then we have constraint programming models or algorithms, which are given in 9 and 10. So this is the first course on data warehousing. So I feel that it is not important, or it is not suitable that we talk about these algorithms in detail. So what I've tried to do in this lecture is that I've tried to give you an overview of the problem and how it is modeled, and I've given you a list of algorithms that are typically used for solving this problem. So if you are interested in this, then you can follow these references and try to understand these algorithms in much more detail. And this is again kind of an overview of the slide or the presentation, and it's a nice presentation given in the survey paper that I'm talking about. And the numbers in the yellow are the references. So you can see that we are looking at 4 different kinds of algorithms here: deterministic, randomized, hybrid, and constraint. And then for each one of them we have the 3 different models as far as constraints are concerned: unbounded, space, maintenance costs. And for randomized we have 2 branches, genetic and this, and then again people have talked about unbounded and maintenance cost, and all 3 for simulated annealing. Hybrid, people have applied only for unbounded, and they've used MVPP here. So these are the kinds of approaches people have. This is a kind of classification of the view selection methods involving the constraints, the candidate selection, and the heuristic algorithms, right? And this is a nice kind of summary of the things that we discussed today. And these are the references that we have I have used in this reference, in this presentation. And of course, not to mention the survey paper, which I mentioned right at the beginning of the lecture. So with this, I come to the end of this presentation, and also I have wound up 3 important subsections, submodules of the module number 7. Those are aggregation, partitioning, and view materialization. And now we are left with only one topic or one technique, that is bitmap indexing, which I'm going to take up next. Thank you.